exactly below the correlation bound. So to show when Q is less than that upper bound, minimax value F3 XRS is not negative. It's enough to show when Q is taken as a correlation bound, the minimax value of F3 XRS is not negative. This is the proof for the lemma 4. Again, it's done by taking chain rules. And this is the proof for lemma 5. This one is also very simple. We just prove it by taking derivatives over x. For the case when Qx is at boundary conditions, we have shown this equation has only one root, and this one root is corresponding to the case when Rxy equal to Pxy. In this case, F3 is equal to 0 exactly, so we have shown the minimax value of F3 is not negative. Then, for Qx is at boundary case, we could let Qx boundary conditions. There are also many boundary conditions, and for Qx, let probability x equal to 0 equal to 0. Then Rxy could be parameterized in T in this form, and by replacing this into F3x Rs, we could obtain this inequality. Notice this, the left-hand side of this inequality is concave over T, so we can get the maximum value by taking derivatives over T. The maximum point is this one, and then we could get the equivalent condition when Qx is at the boundary condition. The Q needs to be less than this expression. Notice this expression. By lemma 6, this expression is exactly below the correlation bound and is still positive. So we have proven one direction, that is, in the case when P and Q are both between 0 and 1, if Q is less than this expression, then the divergence inequality would hold for any Qx. This is the proof for the lemma 6. It's also done by taking derivatives. For the other direction, suppose for any Qx there exists Rxy with Rx equal to Qx, then for the other direction we just need to reconsider the case when Qx is in this special case. Again, we will get the similar inequality, and by this inequality we will get the upper bound for Q mentioned in the result. So we have done the proof for 3 cases, and here is our conclusion. The problem whether the correlation bound is tight or not for the reverse hypercontractive region in binary erasure channel is completely solved when P is greater than minus epsilon over 1 minus epsilon. When P is greater than 2, the correlation bound is tight if this inequality holds, and is not tight. It's only necessary if this inequality holds. When P is between 1 and 2, the correlation bound is tight. When P is between 0 and 1, the correlation bound is not tight. Instead, the upper bound for Q should be like this. When P is between minus epsilon over 1 minus epsilon and 0, the correlation bound is not tight, and this is only a necessary condition. We don't know whether this is sufficient or not. When P is less than minus delta over 1 minus delta, if this inequality holds, then we could say the equivalent condition for Q is this inequality. So thank you for listening. If you have any questions, please feel free to ask me.